All right, check this out. I've got a sea lion who's going to be going into the water over here. He's going on a ramp that is 23 degrees. The distance he has to travel is 3 meters, and the coefficient of friction between the ground and his fat belly is 0.26. That's kind of a reasonable coefficient of friction. I think that, let's see, 0.8 was like rubber, so he's a little bit more slippery than rubber. I think glass was like 0.1 or something like that. I'm not sure, I can't remember. But anyway, he's kind of sliding down this ramp. How long does it take him? Okay, so here's what we're going to do. We have an inclined plane problem to deal with. Let's start drawing the forces that we're talking about. We have the normal, or we have the weight in this case. We also have the normal force, which is pushing up over here. I'm going to make that lowercase n. A lot of times people make it F with sub n. That's fine. That just stands for force norm, or the force of normal. We have friction, and if the sea lion is sliding down the ramp this way, then the friction will actually be pushing this way. I'm going to make that F of k. It's not F of s, because F of k talks about something that's moving. This sea lion is moving down the ramp. F of s would talk about whether or not, like if this ramp were a little bit more shallow and the sea lion weren't even moving. Well, the reason why the sea lion isn't moving is because there's friction between here and there. All right, so I think that's about it. Here's what I'm going to have to do is I have to turn my axes to be this way. It's going to be going down the inclined plane. And I know we were doing this with one force before, where we just had normal force and we had weight, and that was a little bit confusing as to why we would have switched that thing around. But now it kind of makes sense, because if I switch this coordinate system down this way, then this normal force is aligned with the y direction. This force of kinetic friction is aligned with the x direction. So I have more forces that are aligned with my new coordinate system and one force that is not. If I switch this thing, I need to break this into its new components, because my y direction is in this direction, my x direction is kind of going slanted down. So that would mean this. If that's theta over here, then this is theta as well. That means I would have a wx and a wy. Wy is equal to w cosine theta. Wx is equal to w sine theta. Look at that over there. All right. So this is talking about my weight in the x direction, my weight in the y direction. Those are the equations for that. Let's do some of the forces in the y direction. Is equal to mass times acceleration in the y direction. Now, my question that I'm asking you is, well, what's the acceleration in the y direction? You would say, well, it's kind of going down like this. No, it's not. The acceleration in the y direction in this particular case is 0. And you're like, wait a second, isn't he going down the ramp? And I would say yes, but remember, our coordinate system is shifted this way. So as far as our y direction in our coordinate system, this guy is not moving up or down because he's sliding along the ramp right here. He's not coming off the ramp, he's not going into the ramp, he's just sliding along the ramp. That means his height or his acceleration in the y direction is 0. In our old coordinate system, where we had x and y, x going horizontal, y going completely vertical, then yes, I would agree there would probably be some kind of number there. But since we switched it over to our new coordinate system, this guy is 0. This acceleration is 0 in the y direction at least. What forces do you see in the y direction? Well, I see negative wy, because that guy's pointing into the board, or down over this way. And I've got positive normal force, so plus Fn, is equal to 0. So I have Fn equals Wy. And that will come into play. Actually, let's just make it Fn equals mg cosine theta. This is going to come to play later. Actually, pretty soon. Now I'm going to sum the forces in the x direction. That's going to equal to mass times acceleration in the x direction. What is the acceleration in the x direction? Well, not necessarily what is it, but is it 0? That's my question. The answer is no, it's not 0, because this guy's sliding down this ramp. In the x direction, he's actually moving. In the y direction, he wasn't, but in the x direction, he is. And I can't say that his acceleration is 0. I would have to say that it's something. I don't know what it is. In fact, that's what I need to solve for. Because if I knew the acceleration, I knew the length he had to travel, then I could figure out exactly how long it would take him. So I got to figure out what AX is. That's what I'm solving for. Out of all the forces you see in the x direction, I see this WX, I see the FK, and that's the only ones I see. So I've got negative FK, because he's pushing up in the opposite direction of the x direction. And this WX is pulling him down, so it's plus WX is equal to MAX. Now, force of K is also known as mu times the force normal, WX. And I know what the force normal is. This is where this is going to come into play. My force normal is actually mg cosine theta. So I have negative mu mg cosine theta plus WX, which is mg sine theta, equals MAX. The really interesting thing is the M cancels. There's an M in everything over here. I know what my acceleration is. It's AX is equal to G sine theta minus mu G cosine theta. I mean, all I did was I just switched this around. All right. Now that I have my acceleration, I can plug in my numbers and figure out what that is, and blah-de-da. Now that I have my acceleration, I can figure out how long it takes to get to the bottom of this ramp, because I know the distance of my ramp. If I know the distance, I know the velocity. Maybe we'll assume that his velocity initial in the x direction is 0. His acceleration is whatever that is AX from the bottom. His distance is 3 meters. His time is what I want to figure out. Which equation would I use? I think that I would use probably delta x equals v naught t plus 1/2 at squared. It's nice because this v naught is 0, so I can cancel that out. This is d, so d equals 1/2 ax t squared. Solving for t, I get t equals the square root of 2d over ax. And the ax is actually this number over here. So I got my time. It's really the square root of 2d divided by ax, where ax is that. I mean, if you want to write it out in all its glory, you could write it as the square root of 2d over g sine theta minus mu cosine theta. That's your answer. We cool? I know. It looks crazy. It looks tough. It even looks scary. It's not that bad. Let's check the units of this thing. What do I have? I have the square root of 2d. D is in meters. Got it? Over, I gotta make sure I put a big square root of that. Over g, meters per second squared, times sine theta. Sine theta is measured in degrees, but usually when we consider units, it actually has no units. Minus mu. Mu also has no units. Cosine theta has no units. So that's all we have is meters per second squared at the bottom. You take this fraction divided by that fraction. That's not a fraction. Okay, yes it is now. Take that fraction divided by that fraction. You take this one on the bottom, you flip them over. So I've got meters over 1 times second squared over meters. That cancels out with that. And I have second squared, but I have to remember that I was actually taking the square root of this whole thing, so this is equal to seconds. Hey, that's seconds is actually the time that we wanted, because time is measured in seconds. So I would say that this formula right here is pretty accurate. It's pretty good. I'm going to do one more thing with you guys with this equation, and I kind of want to see what your thoughts are. If I were to take a look at this, let's see. if theta, all right, if g got really big, what would happen to this overall number? If I increased g by a factor of 2, what would happen to this thing? Well, what would happen is this g would get really big, making this number really small inside. So you're taking the square root of a smaller number, you still get a small number. So your time would decrease, actually. G got bigger, time would decrease. Now, that's actually makes sense to me, because if gravity were pulling the sea lion down faster, he would take less time to get down to the bottom of the ground. What about d? If d got really big, what would happen? Okay, well, let's take a look at this. If d got really big, then what would happen is this number would get bigger, and the numerator is getting bigger, so the whole number overall is getting bigger. So you're taking the square root of a bigger number, which means time would get bigger as well. Oh, that makes total sense. If this weren't 3 meters, but this were like 10 meters, it would take him longer to slide down the ramp. Well, that's all that's saying. Okay, cool.